Let's talk about the loop invariant in the context of programming. There are many techniques that actually help you debugging your code. Assertion is one of them. Many programming languages offer this technique to help you verify certain conditions during the execution of your code. For example, if you have a while loop, you may want to verify whether precondition holds before the execution of your while loop, and also the post condition after your while loop is done. If one of the conditions does not hold, the assertion can help you terminate your code and tells you what's wrong. Now suppose you have a loop invariant I. By definition, the precondition itself should imply the loop invariant I holds. And then the loop invariant should also be true at the start of each iteration. And after while loop terminates, so here you can see this is not condition, the while loop terminates, and the loop invariant together should imply the correctness of the post condition. So you can assert precondition, you can assert post condition. You can also assert loop invariant to check whether you have the correct loop invariant designed. Okay, so we have discussed, given a pseudocode, how to use the loop invariant analysis to prove or to verify the correctness of your pseudocode. We can also use the loop invariant to help us design the code. So we use this two-color dash natural flag problem as example. In this problem, you're given with array A from 1 to n, consists of red elements and blue elements. We want this array rearranged so the red elements are ahead of blue ones. So this is the problem. And we again use a chart to help us to understand the post condition and loop invariant. So here is my input array A. So at the end, if there are k red elements, I want all the red elements ahead of the blue ones. So if there are k red elements, k should be my boundary between red elements and blue elements. So let's put this as our post condition. So subarray A from 1 to k is red, subarray A from k plus 1 to n is blue. Since we're designing an incremental approach, let's say this is the current element we're looking at. For an incremental approach, we have to assume something, and that is the loop invariant, as we discussed before. We have to assume some fact so that, number one, the fact can become the post condition easily. Two, we assume something is true, and then when we deal with the current element A sub m, we can easily maintain the fact. So one candidate would be, I can assume the elements, the red elements are ahead of the blue elements in the array A from 1 to n minus 1. Okay, so this is one very natural thinking. Can this becomes the precondition easily? Yes, it can. Can this be maintained easily? If I'm dealing with the element AM, and the assumption I have is red elements are ahead of blue elements, so this is very similar to the loop invariant we analyzed for the insertion sort. And then like the insertion sort, we have to find the correct position for this element. And depends on the color. If it's blue, then this is the correct position. And if it is red, then we have to append this to this red subarray. And also like the insertion sort, if we're dealing with a red element, we have to move the entire chunk one step to the right. So it's not very easily maintained in this sense. However, different from the insertion sort, so if we add one more variable to the looping invariant, we can make this maintenance easier. And what is that? Yes. If we keep the boundary in the looping invariant, okay, say the boundary again between k and k plus 1, and then when we deal with this a sub m, if it's red, we know the position exactly, so we don't have to move the entire chunk, we just need to switch the first one element, blue element, with my red element, right? So in this way, we can actually have the looping invariant something like this. At the start of each iteration, the subarray A from 1 to n-1 consists the elements originally from the input A from 1 to n-1, and the subarray A from 1 to k is red, the subarray from k plus 1 to n-1 is blue. Okay? Now, let's actually write the pseudocode to implement this loop invariant. Lines 1 and 2, we need to initialize k and m such that the initialization step of this invariant can be satisfied. Well, at the beginning, the red subarray A from k and the blue subarray A from k plus 1 to n-1, both of them should be empty because we don't know whether the first element is red or blue, so both of the subarrays should be empty. And then the m, the loop invariant, should start from the very first position, so m should equals 1, and k should equals to 0. If we have k equals 0, m equals 1, then both of the subarrays are empty. Okay? So k equals 0, m equals 1. Now, for the maintenance, we actually already discussed the maintenance here. So if we are dealing with the element a sub m, we assume this is true for A from 1 to n-1. We have the red subarray, we have the blue subarray, and then depends on the color of A sub m. If it's blue, we don't do anything. If it's red, we exchange the element of A sub k plus 1, that's the first blue element, and my current A sub m, right? So I have 3 lines of code, and these 3 lines of code can cover these 2 cases and maintain the loop invariant. Okay? The termination step, when the while loop terminates, n becomes n plus 1, so the loop invariant becomes A from 1 to k is red, A from k plus 1 to n is blue, and this is exactly what we want. Okay? So we have discussed the idea of incremental approach and loop invariant. You can read the chapter 2.1 from the textbook. We talked about the design points. So basically, the whole idea is to incrementally build the solution. We also talked about how to verify your algorithm using the loop invariant, and we also talked about how to use loop invariants to design incremental solutions.